Okay, here what we're going to do is take our power series friend for 1 over 1 minus x and play around by integrating and differentiating it to get other power series as well. So just remember, our power series for the function 1 over 1 minus x was the power series from n equals 0 to infinity of just x to the n. And this was true when x is less than 1 in absolute value. Again, this was for convergence. And the way that we talked about this prior was basically by doing this stenciling approach, where we had 1 over 1 minus something. Wherever the x dependence was in our function, we replaced that with open parentheses and did the same exact thing in our power series as well. So whatever we put inside those blue parentheses, we could put inside of our power series as well. But in this case, instead of taking the direct stenciling approach, we're going to ask ourselves, what happens if we integrate and differentiate power series? So for example, if we start off with our power series for 1 over 1 minus x, well, that is equal to the power series again as we have above from, n equals 0 to infinity of just x to the n. And the first thing we're going to try doing is integrating. And if we integrate both sides, well, when we integrate the left-hand side, you could do a slight u substitution here. U equals 1 minus x, du is minus dx, to get the integral of 1 over u times du over minus 1, which eventually will lead you to the ln of u, which in this case is just, minus the ln of 1 minus x. But what happens to that power series when we integrate it? Well, if you remember before, when we first started manipulating power series, we said, you know what? Well, for us in calculus, we're allowed to basically just make this swap of series and integration sign. Again, this is more deeply rooted in real analysis type concepts. But if we do that switch here, that integration only really affects terms with x's, since we're only integrating with respect to x here. And here, well, we can just do the anti-differentiation power rule. So if we bump up that power plus 1, we get this as x to the n plus 1 all over n plus 1. And the last thing we need, since this is an indefinite integral, is a plus c. And well, we found something rather interesting. Take this to the next sheet. We have that minus the ln of 1 minus x is equal to this power series of n equals 0 to infinity of x to the n plus 1 all over n plus 1 plus c. In other words, we know a new power series for a function. We have a logarithm now. So the ln of 1 minus x in absolute values is equal to minus from n equals 0 to infinity of x to the n plus 1 all over n plus 1 plus c. And you might be wondering now, well, how can we get the identity of that integration constant? Well, let's just choose our value of x. Say x equals 0. If we do x equals 0, the left-hand side just gives us ln of 1. The right-hand side will give us this infinite sum of just 0 now being raised to the n plus first power all over n plus 1 plus c. And well, this entire series, since it's just 0 raised to powers in every term, this entire thing is 0. And what we get is c is equal to the ln of 1. But if you really remember your logarithms, the ln of 1 is just 0. So c is equal to 0. So the ln of 1 minus x is actually just equal to this power series of minus the series from n equals 0 to infinity of x to the n plus 1 all over n plus 1. So this is something interesting. We just had to integrate that power series that we started off with, and we found out a power series for a natural logarithm. Who would have thought? Well, let's see what happens if we differentiate now. So if we start off with our power series and function 1 over 1 minus x, it's equal to the power series of x to the n. Again, this is true when x is less than 1 in absolute value. And well, let's come across and just differentiate both sides. Now, if we just remember how we just integrated, this derivative only really cares about things that have x terms within the power series. So we can very easily differentiate that power series, bringing that derivative inside. Just gives us the derivative being now, well, n x to the n minus first power by differentiation power rule. That left-hand side, we have to do a little bit more work. And well, this left-hand side, we get to do quotient rule, which will give us a minus derivative of the top, which is 0, times the bottom, minus the numerator times derivative of the top, which is a minus 1, all over the all over the denominator squared. So in other words, on this left-hand side, that first term is 0, this second term is just a 1, and we get that this is 1 over the quantity 1 minus x quantity squared. And that's equal to the power series now of n equals 0 to infinity of n x to the n minus 1. So again, by differentiating, we can also get other power series relations as well. Now, why this might be interesting is, once we have these types of relationships, we can manipulate them further. So for example, I'm going to rewrite that right-hand side of this power series to look strikingly similar, except there's going to be one difference. Instead of x being raised to the n minus first power, I'm raising x to the nth power. And well, working backwards, what this would mean is, if we had a series where we had n, we had a factor of x, but then we had that other x to the n minus first. So again, we could do this type of algebra. So it looks like we have this extra factor of x hanging out to give this power series on the right. And if we compare this to the power series that's up here, well, what then it looks like is if we insert an x into that power series on the right, we just have to multiply that function by a power of x. So it turns out that if we just take this function that we had before and multiply a power of x onto it, so x over 1 minus x squared, 1 over 1 minus x quantity squared, we're just multiplying an x into that function. So that's like saying, you know what, I'm taking an x, multiplying it into that power series. And with those x to the power terms, I can just combine them. By bringing that power series, or bringing that red x into my series, and since we're now multiplying two quantities, they have the same base but different powers, we get to just go ahead and add those powers. So that's how we can get other types of power series as well. Very much in a puzzling fashion. So we still have this as n times x, now raised to the power of n, instead of n minus 1. So we can start off with functions and manipulate them into looking certain ways by multiplying factors of x after we differentiate, multiplying factors of x squared after we differentiate or integrate, and things of that nature as well.